because the calculations do take time. All right, I wanted to move on to chapter 7. I didn't do too many examples from the calculations, but we did some new ones like calculating the average kinetic energy, the root mean square speed, Graham's law, just the ratio, how much faster something diffuses, Graham's law of diffusion. The van der Waals is you just get the A and the B. And so most of the homework problems I assigned with the van der Waals, and also the van der Waals was a tutorial problem as well, not an end of chapter problem. But that van der Waals problem is just comparing the results you get from the ideal gas law and the results you get from the van der Waals equation. Sometimes the results are very close, so it's really not that critical to use the van der Waals, and sometimes the results are pretty far off, so it would be critical to use van der Waals. The equations, you don't have to memorize the van der Waals equation. That would be given. I would give you like the ideal gas law, but you would have to be able to derive like the molar mass, the variant of the ideal gas law, the density, so you might get a molar mass calculation, you might get a density calculation, you might get both, a molar mass and a density calculation. Usually I'll throw one of those, one or the other, or maybe both in. No, I mean, it's so simple to derive, So I skipped all the derivations from kinetic molecular theory for like Boyle's law and all those. Those are more complex derivations, but the molar mass is very simple to derive. You should be able to derive it quite quickly. I mean, if we look at the molar mass here equation, I would expect you to be able to derive it. Because, like, for example, if you go on and to higher level classes, they're going to make you derive things. And so, PV equals nRT, most people don't need this, but if you do, it's all right. But the molar mass, let's call it M like they did, is mass over N. And then all we do is solve this equation for N. N is equal to PV over RT, and then we just substitute it in here. And so we get M over PV over RT, and then invert and multiply. So MRT over PV. So this is the equation for the molar mass. The molar mass is equal to MRT over PV. So it's like, a less than like a 30-second derivation. So that's why I would expect you to be able to do something like that. And then the trick here is mass over volume. Mass over volume is also the density. And so what we could do here is we could say, I'm going to use their symbol for density. We could say it's the density delta RT over P. So we could do something like that. And so this is like a 1-minute derivation. If it were more complex, maybe I'd just give you the equation. The equation for density is also a 1-minute derivation. So I would expect us, people at Chem 1A level to be able to derive it. You aren't going to have to memorize R. I'll give that to you. No, you don't have to memorize the equation. You don't have to memorize Graham's law or those equations. So those will be given. Van der Waals. I would give you the ideal gas law, but you'll have to derive the molar mass and the density. Okay. And this is just manipulating. We do that a lot with equations. We rearrange the equations to calculate different things. So you give, at least if you do it once or twice, then it's not hard, It's just if you never do it, if you've never done it, you might get confused. You might go down the wrong path or this or that. But if you just do it once or twice before the test, you should be all right, I think. Chapter 6. It's chapter 6. Yeah, I would, the homework, I haven't posted the grades for the homework. I need to post the grades for the homework, but the homework is worth kind of a lot of points. So you shouldn't neglect the homework. And the homework takes time. When I took Chem, they said, okay, you need to spend a couple of hours a day on homework or something like that. And that was literally, I had to spend a couple of hours a day on homework every day. And I did that 7 days a week. So sometimes more, it depends. But I don't, I'll take a look, and hopefully I won't balloon the homework assignment too much. So it doesn't get too crazy. Okay, any other questions? Yeah, take a look at that chapter 6 homework. I put a lot more tutorial problems in that chapter 6 homework than the previous chapters. So I was going to go path A, put a lot more tutorial problems in chapter 7, or path B, just deal with the end of the chapter. If the tutorial problems made any impact, or if they didn't make any impact, I'll just do the end of chapter problems. So that was another thing I was thinking about. So I was asking around. I already asked a number of people what they thought of the tutorial problems, but not everybody. But anyway, we're starting a new chapter here, chapter 7. So chapter 7 is thermochemistry. So what we're looking at is the energy associated with physical and chemical changes or processes. We'll just call them processes. And so as energy. And so just to give you a breakdown, in 7.1 we're looking at some terminology, just some definitions there. And then in 7.2 we'll talk about heat and reaction. Actually, work is introduced earlier, heat and work. And then the first law of thermodynamics, which I'll probably introduce earlier. Do you know what the first law of thermodynamics is? You may already know it. Yeah, that's it, exactly. Energy is neither created nor destroyed here. And so if something loses energy, then something else must gain that energy because it's neither created nor destroyed. And so what they say is that the energy content of the universe is fixed. So we're just exchanging energy within that. And then we're going to look at application of the first law to chemical and physical changes. And indirect determination of, this is supposed to be delta. I don't know why it came out D, but it's supposed to be capital delta. R stands for reaction. H is enthalpy. So this is delta H of the reaction. And we're going to look at standard enthalpies and fuels as sources of energy. Fuels are good reducing agents. If you have a good reducing agent, that's a good fuel. And so what we need to do is we need to combine the fuel with the oxidizer, and then we can get energy from that. So like combusting methane. It's an example of chemical change, a chemical process that we can take advantage of the energy output from that. And then we'll look at spontaneous and non-spontaneous processes. Spontaneous processes have a driving force. Non-spontaneous processes don't have a driving force in the forward direction, but in the forward direction, if it's uphill, then the reverse direction must be downhill. So the reverse direction would have the driving force, so it would be spontaneous in the backwards direction. And so we're going to look at the factors that influence that. And so thermodynamics is a pretty big topic, and so it's broken up into 2 chapters. The first chapter is chapter 7, and it's covered in 1A. And the second chapter isn't covered until 1B. And so in 1B, you primarily look at, we're doing qualitative driving force. The qualitative driving force is, does it precipitate? Does it form a gas? Does it go from stronger to weaker? That's very qualitative. In Chem 1B, you do quantitative driving forces. So you put numbers on how strong the driving force is. And so that's what we'll do there. All right. So when we're looking at energy in chemical and physical processes, physical processes or physical objects or stuff like that, then we need to define things in terms of a system and a surrounding. So this is maybe a little bit different than Chem 4 here. And so the system is defined as the object or process of interest. So system Yeah, I'm going to have a catch-up lecture. I'll post a video lecture this week, probably on this stuff here. So take a look for that. But so when we look at the system, and then everything else is called the surroundings. So when we look at the system in relation to the surroundings, so here we have a system, let's say this is our system, and everything else is the surroundings. But what we see here is that energy, let's say this is a hot beaker, energy can escape this, so you'll feel heat around here. And then if you look, there's steam escaping from here. And so that's water vapor, the matter is escaping. So things are escaping out of our system. Things can enter into our system. And so this is an open system. Energy and matter can be freely exchanged in an open system. So open system, energy and matter can be exchanged or freely exchanged. So energy and matter. When I say freely exchanged, it's freely exchanged between the system and the surroundings. So it can go, back and forth. Energy and matter can be freely exchanged. Between system and surroundings. Uh-huh. The process of interest. It's the subject of the study, let's say. And so the surroundings would be out here. This would be your surroundings. Everything else is the rest of the universe, plus rest of the universe. Uh-huh. Okay. Right. Yeah, we're going to do that, but we're going to look at it step by step. So that's very important. That's very important because if heat is lost, let's say this is a very hot beaker, if heat's lost, then that heat is going into the surroundings. So what is it going to warm up? It's going to warm up like this table, the air, etc. Yeah, we usually call it like exothermic. If it's exothermic for the system, then we say it's endothermic for the surroundings. And then what we do is we put a sign. We have a sign convention. It's like money. Is there such thing as a negative $10 bill? Yeah, can you get a negative $10 bill? But when you look at your account, it could be minus $10. Minus $10 means what? You lost. But that means somebody got plus $10. Who got plus $10? See, so the surroundings got plus $10. You're the system, you lost $10. So that's our sign convention. If one is negative, the other's got to be positive. Or let's say your account balance is plus $10. If your account balance is plus $10, then the surroundings must be negative $10. But is there such thing as a negative $10 bill? No, because energy is like that. Energy, there's no such thing as, there's no such thing as negative energy in this context. It's always positive. It's always a positive $10 bill. The sign, if it's negative, it's just telling you who loses and who gains that positive $10. And so energy is the same thing. So here, the open system, we don't really worry about that. The closed system is the most important. And here, energy is freely exchanged. Energy only. And so matter is not. All the matter is contained in it. You can see there's a stopper here, ground glass stopper. It's an energy only exchange. And then we have an isolated system. In an isolated system, nothing's exchanged. Everything's contained within this. And so no matter escapes, no energy escapes an isolated system. And so this would be like a vacuum thermos. A vacuum thermos is sealed tightly, and the vacuum keeps the heat in. If it were a perfect vacuum, then heat would never leak out. But it's hard to make a perfect vacuum. It's hard to make a perfect vacuum because you know what heat is? Heat. And if when we think about heat, we think about the exchange of kinetic energy from a hot object to a cold object. So a hot object has lots of kinetic energy, a cold object doesn't have much. And then if you bring them into contact, what happens? If you bring them into contact, the hot object cools down and the cold object warms up until they reach thermal equilibrium, until they're at the same average kinetic energy. Because temperature is a measure of the average kinetic energy. And so in the isolated system, nothing is exchanged. Sometimes, actually, we never deal with the open system because the open system is too messy. So primarily, we look at closed systems like this. Sometimes we'll look at isolated systems. But even if we look at isolated systems, then within the isolated system, we'll have a subsystem and a sub-surroundings that we look at. So energy can go out or it can go in. In this case, this is exothermic, so energy is leaking out. But let's say if this were cold and outside were hot, then energy could leak in as heat. You know what symbol we give heat? Q. You give it the symbol Q. But we'll talk about that shortly. So what type of system is this? This would be a isolated system. Isolated system has some kind of insulation around here or something, some barrier to prevent exchange of energy and exchange of matter. If I wanted to make this a closed system, how could I do that? Yeah, I'd have to remove some kind of thing so that energy can be exchanged in and out. And so typically we don't work with this. We work with a system in which the energy can go in and can go out. Now, we're going to look at this in more detail here, but before we do that, let's talk about energy. We're going to be talking about different types of energy, and so this kind of gets a bit mixed up sometimes. And that is, we talk about total energy, internal energy, kinetic energy, potential energy, heat, work. And so we have to define all those terms, or at least have a good mental picture of those terms. And so when we look at the total energy, which we're going to call E or U, we often call the internal energy. The total energy is equal to the sum of the EK. What is EK? Kinetic energy. And then I'm going to call it PE. PE stands for potential energy. So it's the sum of the kinetic energy and the potential energy. And so over here, there's a graph showing it, and then we're going to look at the ball here. Okay, we're going to look at the ball in this position here. So the ball started off up here, and then it was dropped, and then fell down to here. And so kinetic energy is the energy of motion. But what is potential energy? Do you know what the potential energy is? In this case, the potential energy is what we call gravitational potential energy. I'm recording this. Make sure. And the gravitational potential energy is like this. If I put the 3-hole punch, let's say I put the 3-hole punch on the ceiling there, then we say it has high potential energy. It has high potential energy because it could fall and maybe hit you on the head or something if it's not secured, right? And so to lower its potential energy, maybe I'll set it down here on the table, or to lower the potential energy even more, I might just set it down on the floor because maybe I might accidentally knock it off the table and then it might land on my foot. But I'll set it on the floor. And the floor would be the lowest potential energy here unless I drill. I could drill a hole and then drill it down deeper. But eventually to get to zero gravitational potential energy, I'd have to place this where? In the center of the Earth. But we're not going to do that. So what we're looking at is like the relative gravitational potential energy. And relative gravitational potential energy will just be in its relation to the floor. So up here, the tennis ball can fall down. So it has potential energy here. And if it's not moving, it has how much kinetic energy? Zero. And so if we drop the ball, then all that potential energy is converted into kinetic energy. And so this is what we see here. The total energy is all kinetic energy, very little potential energy because the ball's here. There's a little bit of potential energy because it's not on the floor, but it's a little bit above the floor. And then as it moves up, it slows down, right? And so the kinetic energy goes down, and then the potential energy goes up. And so the green ball here, in that position, is here, where the kinetic energy has just gone pretty much to zero. And so this is stopped going up, and now it's about to go down and fall, but it's maxed out its potential energy. So this is as high as it gets here. And then it falls back down, and then we convert it back to kinetic energy here. And so this kind of green and blue one is over here, where the energy is now kinetic. And so we'll be thinking in terms of kinetic energy and potential energy.
What other examples of potential energy will you
Okay, what other examples of potential energy will you encounter? We're going to talk about that, but let me just briefly talk about this first, and then we'll look at some more examples. So, do you know what units are typically used for energy? Joules. And chemists use joules much more than calories. Joules is the SI unit. It's kilogram meter squared per second squared. That's the definition of the joule. And so there are different ways of thinking about the energy unit here. One way is thinking in terms of kinetic energy. This is what we call translational kinetic energy. So this would be the kinetic energy of the tennis ball there. And then Do the tennis balls vibrate? You know, are they vibrating?
No.
Not really.
Right.
And then if they're spherical, then we don't say they're rotating. It has to be a non-spherical shape to have these rotational things like this. You know, the ball could be spinning, but it looks exactly the same. And so it doesn't really. Okay. Or we could add spin to it because there's people who spin it and then try to get it to do different things. We're not going to get that complicated. And so this kinetic energy is only what we call translational kinetic energy. What other types of kinetic energy do we have? For more complicated systems, we would have, in addition to for more like complex molecules, I should say for molecules, the kinetic energy is equal to the translational kinetic energy plus the vibrational kinetic energy. So this says translational, this is vibrational, plus the rotational kinetic energy. And we know one other thing about the kinetic energy, that is the E bar K is directly proportional to what? It's directly proportional to, not the potential energy. This is a way to measure how much kinetic energy. Well, if we're at absolute zero, is there any kinetic energy? No. If we heat it up, what happens? We get more energy. And so it's directly proportional to the Kelvin temperature. So if we want to know how much kinetic energy there is, just measure the Kelvin temperature and we can determine how much kinetic energy there is. And so we aren't going to calculate the kinetic. We did calculate kinetic energy using this, 1/2 mv squared or 1/2 mu squared RMS to get the average. Remember? But we're not going to do this kind of calculation here. It's just so you should know. That's kinetic energy. But we can also do work. Work takes energy. And so, for example, if I want to lift this 3-hole punch, it's kind of heavy, but if I want to lift this 3-hole punch to the ceiling, that's going to require work. How much work does that require? Well, the amount of work that's required, do you have it yet? MGH, right, that's good. It's going to depend on force times the distance. The force of having to push this up there and how high up I do it. And so this is talking about mass times acceleration, that's the force, times the distance. And so the units here would be masses in kilograms. The acceleration is given in units in meters per second squared, and the distance is given in meters. And that's going to be in joules also. And so what I want to talk about here is this. I want to talk about the kinetic energy and the gravitational potential energy, which Gavin had mentioned. So gravitational potential energy is going to equal the mass times the acceleration. The acceleration is g. G, do you guys remember what g is? Yeah, this is the gravitational constant here times h, mgh. And so that will be the gravitational potential energy. So just to go back here, in order to calculate the gravitational potential energy of the tennis ball up here, all we would do is we would just take so this would be the PE, which would be the mass of the tennis ball times G, which is 9.8 meters per second squared, times the height. The height, I don't know how high this is. And that would give us the gravitational potential energy. And then to calculate the kinetic energy down here, we would use the other equation, 1/2 m u, because this book uses u instead of v. Most books use v, 1/2 mv squared or 1/2 mu squared. And so we could get the combination there. G is the gravitational constant. Which was what, 9.8 meters per second squared. Most people just have it to 2 sig figs. We could go more. You could go more sig figs if you want. But it's easier to remember to 2 sig figs. Do you have it? How many sig figs do you have it memorized to, Gavin? The G. What do you have? G.
It's like 9.806.
Okay, yeah, that sounds right. 9.8066. And so we can do another example of this kind of system. And so an often used one is, let's say you're on a playground slide and you're at the top of the slide, but you're not moving down yet. Then what is your total energy? Okay, U is equal to the kinetic energy, E sub k, plus the PE. Here. And let's say we're at room temperature here, RT. Okay, this is U initial. If you're not moving and you're just sitting there stationary, do you have any kinetic energy? No, so the kinetic energy is 0. And this is all potential energy. And this potential energy is just equal to the mass of times G times H, mgh. It depends on how high you are. You know, the higher you are, and the more mass you have, or the more you weigh, mg is how much you weigh in newtons. How much you weigh in newtons? 1 newton, which is a kilogram times g, 9.8 meters per second squared. 1 newton is about a quarter pound. And so it's kind of, the force is in newtons, which is about a quarter pound. But anyway, it depends on how much you weigh and how high up you are. That's how much potential. So if you're, let's say, 50 kilograms versus 100 kilograms, you know, you're going to have a lot more potential energy. It's going to take more work to get 100 kilograms. The amount of work is the same. It's going to be mgh because you're starting from here, and that's the amount of work you're going to have to do to climb up the stairs to get to the top of the slide. Does that make sense? Okay, as you slide down, what happens? As you slide down, you end up at the bottom of the slide. If you end up at the bottom of the slide, what's the U final here? U final is equal to the kinetic energy plus the potential energy. And let's say you stopped at the bottom of the slide. If you stopped at the bottom of the slide, then what is your kinetic energy? Again, it's going to be 0. But what is your potential energy? Your potential energy is going to be mgh. And so you see H1 is a lot taller than H2. And so H1 is a lot bigger. So therefore, your potential energy at the beginning, mg is the same. Your potential energy at the beginning is much higher than it is down here. So what happened to all that energy? Because the first law of thermodynamics says that energy is neither created nor destroyed. So where did that energy go? And so this is called the system. You're the system, and this is what we call a process. The process is going down the slide. And so we did this physical process, slide down the slide. What happened to all that energy? Well, it depends on how you got down from the slide. So for example, if you didn't go down the slide here, and maybe you jumped off the top, you might have had an impact. And that impact may have put all the energy into your ankle bone or whatever, or bone. And you might have twisted your ankle or broken the bones, right? And so all that energy here could have been converted into the energy required this is the energy of work, the mechanical work of breaking bones or straining ligaments, that kind of thing. But let's say you went down the slide and you didn't break any bones. Then what happened? What happened to all that? I'm sorry? Friction. And then the friction leads to, you probably feel it in the seat of your pants, it leads to what? Heat. And so probably as you're sliding down this slide, you're losing energy as heat. And so probably the slide, if you touch it, it's a metal slide or plastic slide, it's probably warm on the surface after you slide down, and probably your pants are warm. And so what we generate is we generate heat. Heat is Q. However, the energy could have been lost another way. So let's say you slid down this, but let's say you accidentally fell. If you accidentally fell off the top of the slide and ended up breaking a bone here, then did you generate much heat? No, I mean, if you go down the slide like this, you're going to generate a lot of heat, but if you fall off the top and end up breaking a bone, then you feel that much heat. Maybe you'll feel some heat, of course, from the swelling and whatever else, but that energy there was not lost as heat like here. The energy was lost as, what do we call that? What we call that is the energy would be lost as work. Work is given this symbol, W. Or you might have a combination of, since the first law, energy is going to be conserved, it could be a combination. So it could be all heat, no work, or it could be a combination of heat and work, or it could be a combination of just work. There's another way to try to get more work, less heat out of this energy change, and that would be something like this. Let's say on this slide here, you lubricate the slide with oil, let's say, vegetable oil or something. The oil is used to reduce friction. And then you tie a rope around your waist, and then you hook it up to a frictionless pulley. And then you have a weight at the bottom here, and the weight at the bottom weighs about as much as you do. And then you go down the slide. And so if we go down the slide here with this weight, we're going to go very slow. And so we go very slow, and then at the end of this, you're going to be at the bottom. Down here. And the weight is going to be where? yeah, the weight's going to be at the top. And so all this potential energy that was lost in, did you generate much heat going down this? We say we go down this like infinitesimally slow, super slow, doesn't generate much heat. This is frictionless pulley, and then we pull this weight. And so did we generate much heat? No. And in fact, what we did was we tried to maximize the amount of work. So here, work was maximized. You know, this is idealized. You'll probably generate some heat nonetheless. But we just tried to maximize the work. And how much work did we do? Well, the amount of work that we did was, you know, mgh. You know, how much does this weigh? G is constant, and then the height, you know, how high that is. That would be it. So this would be another example of that.
So what equation would you use for that if you're climbing the ladder? Is that the math?
Yeah, the equation that you'd use for climbing the ladder would be the same. It would be mgh, because the thing that we do here is, you know, we don't monitor this continuously. Like, obviously, you know, you can watch the person slide down the slide, they generate heat, and then they get to the bottom. So it's a continuous process. But what we do is we just look at where they started, that is the initial state, and where they ended, the final state. And if we only look at the initial and the final, and not necessarily how they got from initial to final, you know, you probably can tell, you know, if they're laying on the ground in pain and they have a broken bone, then you probably can tell they probably fell off that. They probably generated a lot of work, but probably not much heat. Or if they're sitting over here, then you probably know that they did that. But what we do is we do this. We just look at the final and the initial and the difference in energy. So if we calculate the difference in energy, which we would call delta U. How would we calculate it? We do delta U. So delta U is equal to U final minus U initial here. And then we would do, okay, this would be the initial height here. This would be the final height here. And so we could simplify this equation a little bit by factoring out mg. So I'm going to factor out mg, and it's just going to be the final height minus the initial height here, and then I can calculate, you know, how much. And so that would be the same as climbing the ladder, you know, except climbing the ladder, you know, what we have to do is we have to pay attention to the sign convention. And the sign convention we're going to run into quite a lot. And so it's like, did that cost you energy to climb the ladder, or did it release energy in climbing the ladder? And so, in other words, is it like endothermic or exothermic in this process? And so then we keep track of signs, but the way we keep track of signs is by the equations that we'll have. To climb the ladder? Yeah, you would be losing energy. It would cost you energy to the system.
How do you measure work?
How you measure work would be like this. This is gravitational work. You know, gravitational work is you have some kind of reference point, which we'll call zero. And so if the playground floor, we'll just call that arbitrarily zero gravitational potential energy, because the true absolute zero gravitational potential energy would be at the center of the Earth. So we call that zero, and then we figure out what the difference in energy is, and that's how much energy is going to cost you. And so you just calculate it using MGH. But we're not going to do this because do chemists worry too much about gravitational forces? No. I mean, we're not going to be doing a reaction at the top of the slide and let the reaction slide down. The beaker slides down here and generates some heat, and yeah, we're not going to do that. And so what we're going to do is we're going to look at a more a chemical system. And so when we look at a process, actually, let's take a look at some examples here. of this. When we look at systems, systems can be objects or processes. What I can say is we could say and processes. You know, we could have an object undergoing some kind of process, and I'll talk more about what I mean by process. A process is going to be like a physical or chemical change, and so it's going to be physical or chemical change. Can you give me an example of a physical change? Oh, like the translation? Yeah, I mean, that would be a physical change, but in terms of what we were talking about in chapter 1, uh-huh. Yeah, like water going from solid to liquid, and we call that change what? Yeah, that would be a physical change because it's still water. You have water in the solid state, and it's still water in the liquid state. But that change in going from a solid, that is ice, to liquid water is called melting. It's called melting. And then there's a fancy name for melting. Do you know the fancy name for melting? The fancy name for melting is fusion. Have you heard of that? Delta H of fusion. What's that? There's things like that, latent heat of fusion. So you've heard of fusion before. And then there's nuclear fusion, which is totally different. Nuclear fusion and fusion, like in melting, are two totally different things. And so physical changes would be like melting or physical process melting. What's another one? Boiling. And these ones we term as phase changes because the phase is in the solid phase, the liquid phase, or the gaseous phase, or the plasma phase. So we call these phase changes. And so that's what I'm talking about in this. Although like translation, if a molecule translates from one position to another, you could call that a change as well, but it's not this type of change that I'm considering here. That would be more just like kinetic energy. How about a chemical change? Give me an example of a chemical change. Combustion. Combustion is a good one. What else? pH is more of a physical property because if you stick a pH meter into, let's say, apple juice or something, is it going to change anything? In a chemical change, what you start off with initially is different than what you end up at the end. There has to be, like when you combust something, like combust gasoline, is it still gasoline at the end? But pH is something that can be non-invasive. That is, like for example, if you want to measure the pH of a cell, do you have to burn it up, or hopefully you don't have to break it? But people are trying to measure the pH of the intracellular fluid without breaking the cell membrane or something like that. They're trying to be as non-invasive as possible. And so pH would be more of a physical property. Any other chemical? What's that? Rusting. Rusting is what type of reaction? Yeah, oxidation, reduction. What's the oxidizer in rusting? Oxygen in air, right? And what's the reducer in rusting? Rusting is usually for what metal? Copper can undergo oxidation too, but we don't call it rusting. Rusting is usually reserved for iron. So actually the protecting iron from rust, I mean, if you visit certain like rust belt places and you see lots of rust, like where it's humid, the environment and stuff, like in Japan, there's lots of rust, lots of corrosion. So a lot of money spent to try to prevent rust. So you can't. I guess you can remove, oxygen and whatever else, but um, for small samples, but not anything practical.
Are redox reaction, like is it combustion in the type of
Combustion is redox also. Yeah. That's why, if one, I used to use some powdered metals, and on the powdered metals, there's a warning on the bottle. And this was a bottle of powdered copper. The bottle of powdered copper said flammable on it, and so it was a hazard, a fire hazard. And you think, wow, copper metal, it doesn't seem to burn. But if you have it in the powdered state, then it's much more can combust much more easily. And this goes the same with like flour. Flour burns, but if it's in finely divided powdered state, it burns much easier. Especially and so you have those grain fires or powdered sugar versus granular sugar. Powdered sugar burns or combusts much easier. And so yeah, combustion is oxidation.
radioactivity?
What's that?
Radioactivity?
Radioactivity. Yeah, radioactivity would be because we divide it into nuclear and chemical, and so that's more of the realm for nuclear chemists and nuclear physicists, the radioactivity stuff. And so that for sure is a change, but it's a nuclear change. The actual nucleus is changing. In chemical processes, the nucleus doesn't change. The atoms are just rearranged. And sometimes the atoms are just more than rearranged. In metathesis and acid-base reactions, the atoms are rearranged. But in redox reactions, in addition to being rearranged, the atoms can be, yeah, the electrons, we're going to lose electrons and gain electrons. And that results in high energy. So in like metathesis or, the double replacement, in acid-base reactions, the energies when you rearrange these atoms aren't so huge. So redox reactions, you have potential for violent reactions. You have the potential for violent reactions because when you look at the stability of things like sodium metal versus sodium ion, there's a huge difference. And so when somebody says, "Oh, I got to cut down on my sodium intake," they're not talking about cutting down on eating sodium metal. They're talking about cutting down on eating sodium ion. Sodium ion's stable, but sodium metal is one of the more powerful what? One of the more powerful reducing agents. It's not the most powerful. What was the most powerful reducing agent on the chart?
Solid lithium.
Yeah, it was the lithium. Was the most on our chart. Right? Whereas sodium ion was it very reactive. Sodium ion was listed as so if sodium metal is very reactive, that means its conjugate sodium ion must be stable. Sodium ion is pretty stable. It's fairly unreactive.
What's another chemical?
Yeah, that's a chemical change. So in the redox reactions, we have to be, with the acid base too. The strong acid and the strong base, we got to be careful on mixing them. What was that safety rule we talked about? Yeah, add acids. And so you got to be careful. But in redox, you got to be extra careful, because people have been killed from violent redox reactions. I think at the University of Hawaii, it wasn't that long ago, that there was a hydrogen explosion there, and that was hydrogen. And, when you look at hydrogen, how strong of a reducer is hydrogen on the chart? Do you recall where hydrogen was positioned on the chart? Was it one of the more powerful reducers, or was it kind of mid-range? Or moderate? It was moderate. And then oxygen is not one of the most powerful oxidizers either, but that was a very powerful explosion. Which we'll see a demo of coming up.
So what's another chemical?
So we have combustion, which is a redox reaction. We have redox reactions. We have acid base, right? Like, what's that? Rotting, like decay, like yeah, for sure. Fruits rotting. Right. It's chemical because it's changed the identity of the thing. I have a whole bunch of rotten strawberries right now that are rotting. Unfortunately, I bought way too many. I should have brought them in.
This is also release chemicals, right?
It could, yeah, that could. Now, in an open system, those chemicals would be released into the surroundings. But if we keep a closed system, then we can make sure we capture the chemicals that are released. And so in a closed system, the products would be contained.
Your fridge smells like rotten strawberries.
Yes. Yeah, the fridge smells like rotten strawberries. But it's not that bad. It just smells like fermented fruit right now. But there's puddles of strawberry stuff in there. It wasn't as bad as the vinegar wine that I had.
Oh, yeah, the wine.
What's that? Yeah, that had a very bad smell. So, yeah, that's something I'll never forget. Was that I thought it was such a bargain. But anyway, so the process is the thing about processes are they have a finite life to them. And so this is a process here. Sliding down the slide. Sliding down the slide. Once you slid down the slide, are you sliding down the slide anymore? No, it's sliding down the slide is a process and it has a finite life, and then after you slide down, there's no more sliding down the slide, right? It's done. And so once you slide down the slide, then what's going to happen is energy. This is going to be a closed system. Energy can be exchanged, and so we lost energy. The system loses energy, and then what must have gained the energy? The surroundings must have gained energy. And so we can figure out how much energy this surroundings must have gained by the first law of thermodynamics. The amount of energy the surroundings must have gained is equal to the amount of energy the system lost. And the system can lose energy either as heat and or work, depending on how you got down from the top of the slide. It's like the same thing. After your ice cube melts, then your system is gone. If your system is the ice cube melting, and your system is, okay, how much heat or how much energy does it take to melt that ice cube? And so you input all that energy and the ice cube melts. Is your system there anymore? No, the system is just the melting of the ice cube or the boiling. And when you combust gasoline, the gasoline is no longer there. It's when you burn up all the gasoline, there's no more gasoline left. And so the system originally had gasoline in there and air, but it's no longer going to have that. This is different than if the system were an object. Let's say you have 100 grams of gold, solid. And let's say this gold is at 250 degrees Celsius. And so you have a hot, if I had 100 grams of gold, that would be really nice. But let's say you had a hot gold bar. If you had a hot gold bar, then what can happen to that? And so this is a little bit different. And so what usually happens with an object is objects typically either heat up or cool down. And so we'll be looking at this. And so this could get hotter or this could get cooler. So let's say it cools down to 25 degrees Celsius room temperature, or let's say it warms up to 500 degrees Celsius. So if I cool the gold bar down to 25 degrees, do I still have the gold bar? Yeah, the gold bar is there. That's the system here. The gold bar is the system. The gold bar was originally at 250, now it's 25. Or if I heat it up, I add energy. So here I have to remove energy in order to cool the gold bar down. Here I have to add energy in order to heat up the gold bar. So we'll have that deal with. And so let's look at another example of this, which would be, the gold bar. If we melt the gold bar, then that would be a physical process, the process of melting. So we're going to take a look at this here. Let's say I have 500 grams, or not 500, let's see, how many grams? 50 grams. Let's say I have 50.0 grams of H2O liquid at 100 degrees C. All right, so I have 50.0 grams of H2O liquid at 100 degrees C. I'm going to remove energy from this. If I remove energy from this, what's going to happen to the H2O liquid? Well, I'm just going to cool it down. Let's cool it down. Let's say the surroundings here. So my system, this is going to be my system here. And in this case, my system is an object. Just the water here. So I remove energy, so minus E here. And where's that energy going to go? Into the surrounding. So let's say my surroundings were at 25 degrees C, room temperature. And eventually this water should cool down to what temperature? 25 degrees C, room temperature. Because heat is the transfer of kinetic energy from the hotter to the cooler. And we're going to say the surroundings is going to be a big heat sink. So there's plenty. Sometimes the surroundings will warm up, but if we have a huge heat sink, then it kind of stays. I mean, the heat is dissipated throughout the rest of the universe. And so we're going to go to 50.0 grams of H2O at 25 degrees C. And so the way we look at this is like this. I'm going to have what we call an energy level diagram, in which I'm going to put the energy here, the total energy, U, which we call the internal energy. And then up here, I'm going to put 50.0 grams of H2O at 100 degrees C. And then U is equal to what? The total energy, or the internal energy, is equal to the sum of the kinetic energy plus the potential energy, PE, so EK. And this is going to be initial, so I'm going to call this U initial, EK initial, PE initial. And then what I'm going to do is I'm going to remove energy here. And where's that energy going? To the surroundings. So the system will have a loss of energy, and the surroundings will be positive. And so this we call delta U. And then I'm going to be down here at 50.0 grams of H2O liquid. This is H2O liquid at 25 degrees C. And so U final is equal to the kinetic energy final plus the potential energy final. And so normally when we think about potential energy, gravitational potential energy comes to mind. But is this, even though I drew this lower, it's not gravitational potential energy we're talking about because this is just a beaker sitting on a countertop. And so there is no drop in gravitational potential energy. So what is the potential energy of water then? If we're ignoring gravitational potential energy, which we do, we're going to ignore gravitational potential energy, then what is the potential energy of water? And the answer to that is what the potential energy is we call this chemical potential energy. And so, what is chemical potential energy? Well, qualitatively, it's like this. It has the potential to do something. So, for example, when I think about chemical potential energy, I worry about redox reactions because redox reactions can have the potential to do a lot of damage, you know, versus like let's say a lot of precipitation reactions. With precipitation reactions, I really don't worry about it exploding, or causing much damage. It's just, you get a nice precipitate, it looks nice. Acid base, you got to worry. That's why we have the safety rule: add acids because it could cause a lot of heat to be generated. But redox, we got to really worry about the potential. And so to get an idea of chemical potential energy, you would think, a lot of people are worried about hydrogen cars because they're worried about the chemical potential energy of hydrogen cars. So if you have a tank of hydrogen gas underneath your seat, are you going to feel comfortable? No, not at all. I wouldn't feel comfortable at all. And so I was at this conference and I was talking to this guy. Who's also a chemist, and he got one of the first hydrogen cars from Mercedes Benz. And I asked him, "Well, aren't you uncomfortable having a tank of hydrogen?" He said, "No, because he's told me this before he decided to lease it. They would only lease it; they wouldn't sell them. They showed him a video of them dropping it from I think like a 747 at 30,000 feet or something like that." Dropping it from that high of gravitational potential energy, and they dropped it in the desert, and the tank didn't explode. And so he said after that, he felt comfortable. I don't know, it was 30,000 or 60,000 feet, but I still thought, what if, what end hit the ground, or, maybe they weighted one end more than the other, or did it hit the valve, Is when you work with compressed gases, you have to go through all kinds of safety courses because if the compressed gas, the valve breaks or something, then it just blows all the air out of the room. But I was thinking, if it blows all the air out of the room and fills it with hydrogen, then that's pretty bad. But he felt comfortable. So. And then I test drove one of those. I think I told you about this. They were offering test drives in Manhattan Village. And if you test drove it, they give you a $25 Simple Green. So I saw a $25 Simple Greens. I'll test drive it. And it was like the Toyota Mirai, which is the hydrogen car. But it just drove, it was a hydrogen fuel cell car. So it just drove like an electric car. What was that? The experience was, it was like, because I have an electric car too, so it's just like driving any other electric car. Electric cars are nice because they don't make much noise. They don't have a combustion. Well, they do have oxidation but it's oxidized not to generate mechanical work. In a combustion engine, you generate mechanical work with the pistons. But in an electrical vehicle, you generate electrical work, which is then converted into mechanical. So
does that mean that you're scared that you
no, I was thinking about leasing a hydrogen vehicle because they were giving free hydrogen. But the problem is I've heard a lot of complaints because there are other people who have them, and they were complaining that the price of hydrogen has skyrocketed. It's so expensive to fill those, and so there's a bunch of lawsuits happening right now, which is unfortunate. The hydrogen economy, the original plan from the state of California was to have like 400 hydrogen filling stations, and I think there are like 3 or 4. I mean, around here, there's one on 190th, there's one on Prairie, something like that. There's like grand plans of having building all this hydrogen infrastructure, which didn't pan out. But still Toyota is betting, and other companies also are betting on a hydrogen economy. But now Toyota, I think, switched to ammonia. Ammonia. We were talking about ammonia earlier. Ammonia is a good reducer or a good oxidizer. Ammonia is not on our chart, but this was from the side. This is from earlier. Do you remember this? Well, how can we tell? Is this electron rich or electron poor? It's poor? Well, the first thing we do is, if we don't see it on our chart, then what we might do is we might take the oxidation states. What were the oxidation states here? So hydrogen versus nitrogen, which one do we assign? Hydrogen's +1, nitrogen is 3. And so what they want to do is, this has chemical potential energy. This is chemical potential energy because this is electron rich or electron poor. Well, hydrogen is kind of, you've seen hydrogen with +1, like in water, hydrogen's +1. Well, what we want to focus on is the nitrogen. When you look at nitrogen, what's the range of oxidation states for nitrogen? Not -5.
Okay.
+5 to, is it on the more negative end or the more positive end of that range?
It's more than
More negative, so this is more electron rich. So we call this electron rich, like methane. Methane's pretty electron rich because carbon is in the -4 oxidation state there. And so these electron rich species are good fuels. Good fuels have chemical potential energy. So it could just be sitting there. You could have, let's say, a cup of, actually methane's a gas. You could have a tank of methane gas. It's easy to liquefy, not methane, sorry, ammonia. It's easy to liquefy ammonia. But you could have a tank of ammonia gas, and that could be sitting at 25 degrees C. And so it's at 25 degrees C, does it have much kinetic energy? No, I mean, just room temperature. But it does have potential energy because that ammonia can actually combust. That ammonia can burn. That ammonia can be oxidized to form oxides of nitrogen. Do you remember some of the oxides of nitrogen covered? What were some of the oxides of nitrogen? So if we burn that in air, we'd form oxides of nitrogen. This is why I thought this was a failure idea. I thought this was a failure idea because it's going to be creating NOx. And NOx are a big problem. NOx are why NOx are why VW and Mercedes and all those got rid of diesels. The diesels were producing too much NOx. So they had some kind of chemical technique to get rid of the NOx. But it turned out that maybe you heard about what happened to VW? Well, VW, what they have is they have different engine mapping things that they put into the ECU, which is the computer of the car. And so when they went for the NOx testing, they put in a different map, a map that was totally like undrivable. And apparently they got caught because they have to go before CARB, the California Air Resources Board, for emissions and that kind of stuff. And somehow they were caught. They thought maybe it's legitimate. They can alter the map and then bring it in for testing and then put in a different map which generates a little bit more NOx. I don't know how much more. And be good with that. But it turned into a big deal. And it was a huge settlement. And the huge settlement resulted in, this is my understanding, resulted in the Electrify America. Have you seen those Electrify America charging stations around? I think those are all paid for by VW as part of the settlement. I could be wrong. This is what I was told. I haven't actually looked at the original stuff. But anyway, getting back to this, ammonia has chemical potential energy as a fuel. And so this is what we think of in terms of chemical potential energy. We don't think about gravity. We think about that, we think about this. And so this is a fuel. So why I thought Toyota was going to fail is how are they going to get rid of all the NOx? If you combust this with air, you're going to generate lots and lots of NOx. And, when in California, your car has to be smogged every 2 years and they measure your NOx emissions. If your NOx emissions are too high, then they won't renew your registration. What's that?
They won't register that.
Yeah, they won't register. So I used to always worry about that because I used to drive really old cars. Really, really old cars are exempt from smog. I think this is just my opinion, but I think rather than pushing everybody to go electric, if they get rid of some of these gross polluting old cars and make it more feasible to buy a new car, new cars pollute so much less than old cars, even cars from like the 90s.
Water is not either strong or...
Yeah, right. Does water have much chemical potential energy? I mean, if you think about it, is water a good fuel? Is it easy to burn water? No. It doesn't have it. So we say water is relatively stable, right? And so we have other things that have high chemical potential energy, and those things are the potential to react, the potential to change.
So then how do you measure your potential?
Well, we measure it in relation to what we're trying to do with it. And so it's always relative. It's the chemical potential energy relative to what? And so here, what are we doing? We're going from 50 grams of water to 50 grams of water. So did the potential energy change at all? No, the potential energy didn't change at all. What changed? The kinetic energy changed. And so when we look at this here, the potential energy initial is equal to the potential energy final. And so the only thing that changed is the kinetic energy. The kinetic energy, the average kinetic energy can be measured by the temperature. And so it's obvious the average kinetic energy changed. Here we're at higher average kinetic energy, and here we're at lower average kinetic energy. So in this case, when we have objects, if you have an object, a bar of gold, initial, hopefully it's still gold after. Otherwise, that's a very expensive experiment if it changes chemically, right? And so usually with objects stay the same. So this is 50 grams of water, this is 50 grams of water, it's an object. And objects stay the same. The only thing that happens is that since the potential energy doesn't change, only thing that can happen is the kinetic energy changes. If the kinetic energy changes, then the only thing that can happen is it either gets hotter or it gets colder. And so when we think about objects are either going to heat up or cool down. In this case, the object is cooling down. Our system is 50 grams of water. The 50 grams of water is cooled down. And so when our system is an object, the 50 grams of water cooled. We have an equation for this. You might have seen this equation before. Q is equal to mc delta T. Have you seen that equation before? Q is equal to m cap, mc delta T. And so when we have objects, They either heat up or cool down. That's delta T. If delta T is negative, it cooled down. If delta T is positive, it heated up. What if we add energy? I'm going to add energy to this. What's going to happen to 50 grams of water so add energy is I'll just take the burner or the hot plate and just add more energy to this. What's going to happen to the water? Yeah, is it going to heat up? Is it going to get hotter? Can I heat water up to, let's say, I want to heat it up to 150 degrees C. Is it possible to heat the water to 150 degrees C? It is in a pressure cooker. Have you seen those pressure cookers? Why people like pressure cookers is because they can get hotter water. And so let's say you're boiling pasta. If you boil pasta in a pressure cooker, do you know it boils faster? I mean, no, it doesn't boil faster. You know it cooks faster. Do you know why it cooks faster?
Because the gas stays inside and the temperature and the time stays inside the pan. Because it's cold, it's not just releasing it on its own.
Yeah. Well, the main reason that's part of it, because it traps in the heat and the matter in there. You know, you don't have steam leaking out, which is energy leaking out, and that kind of stuff. And so that's important component of it. But the other reason is because the temperature is higher. Water boils at a higher temperature at higher pressures. And so pressure cookers, they cook faster because you can get more than 100 degrees C. A little bit more, not much. Exactly. Yeah, the higher the temperature, the more kinetic energy, and your food is going to get hotter faster, that kind of thing. The other thing is like high altitude. Have you ever tried to boil a pasta at high altitude? You know, you have to add time because it takes much longer to boil because water boils, let's say in Denver, water is boiling at 95 degrees C. It's going to take longer to boil than 100. I mean, not boil pasta, cook pasta. And so it depends. And so here, if we add energy, we have boiling. Water boils. Well, and so let me just do this. When water boils, does the temperature change? Yeah, as the water boils, the temperature doesn't change. And so water boils at 100 degrees C. And what we're going to form is we're going to form H2O gas at 100 degrees C. And so the way we like to represent these, over here, this is an object. Over here, this is a process. And so I'm out of time, but next time, or on this video, I'm going to do a video thing. We'll talk about how we represent this object and process. Oh, yeah. Okay, let me hand this back. The retake for the test. I'll probably be faster.